Mason Schuler. This is Kevin Alvarez, as well as Jason Katseros, and we are Team 13. We worked on object detection of a diverse object data set. So our goal was to create an accurate model that could detect objects in real time. So by that, we wanted to create a model that could detect the location of different objects from different classes in an image. So for example, we have this picture here that contains multiple objects from different classes, and we're highlighting the region of the image that those classes occupy. Our motivation was that object detection can be applied to many tasks and domains, such as autonomous driving, robotics, search and rescue missions, etc. And we're particularly interested in building detection systems for robotic applications. Because of this, our network needs to be fast and accurate, as well as capable of recognizing a diverse set of objects. Because of this, we picked the open image dataset v6 with bounding boxes, which contains around 2 million images as well, which containing 16 million bounding boxes. The images range from fairly simple with not very many objects per image to fairly complex like the image in the center. It contains lots of objects from multiple classes with the objects overlapping one another. Because the data set's so large, we decided to restrict ourselves to use only the validation set, which contained around 42,000 images, 304,000 bounding boxes, and 500 object classes. We chose to split this into 70% training data, 15% testing data, and 15% validation data.
Our experimental design. So we built two different models. The first one was a deep end-to-end convolutional neural network, and the second one was a simple baseline for comparison. For the neural network, we used a single-shot multi-box detector model. And for our baseline model, we used a logistic regression image patch classifier, which used histogram of oriented gradient features. And for detection, we use a sliding window approach with an image pyramid. We'll talk more about that in a few slides. So once we have both of these models trained, we calculate the mean average precision on the test set in order to do the comparison. So the single-shot multi-box detector starts with a pre-trained base network and then replaces the end of this base network with the SSD detection design. So for us, we use a pre-trained VGG16, which is a powerful image classifier, pre-trained on the ImageNet for classification. So this was pre-trained on a large amount of images. We take this base network and we replace the fully connected layers with convolutional layers. The SSD is a fully convolutional network. So essentially what we're doing is we're using the base network as a powerful feature extractor and then adding on layers to the end of this to modify the network for the detection task. So the added layers on the end alternate between 1x1 convolutional kernels for dimensionality reduction and 3x3 kernels for feature exploration and spatial reduction. We also add localization offsets and confidence heads to make predictions from feature maps of each of the 3x3 kernels. And these themselves are also convolutional layers that generate the actual predictions. So a core idea for a SSD is default boxes. So the model starts by building a large set of these default boxes. For us, we use over 10,000. These default boxes vary in size and aspect ratio and location in images. So this is just a very small subset from our 10,000. Each prediction head in SSD is associated with a subset of these default boxes. Each subset has boxes at a particular scale. Deeper into the network the prediction head is, the larger the scale of its associated default boxes. Each box in a subset is also associated with a particular feature map cell for that prediction head. And for each cell, there are 6 boxes at varying aspect ratios. What this gives us is a rich set of powerful default boxes that vary in size and aspect ratio. And this allows us our model to predict objects of different sizes and aspect ratios. So the way the model works is that the outputs are tied to individual default boxes based on the prediction layer and the feature map cell. And the model outputs location offsets to modify the default boxes to better fit the nearest object, and also outputs probability distributions over all class labels for that box.
The loss function for the SSD network, it consists of both a confidence loss, which is the softmax between the class predictions with the actual class labels, and a location loss, which is the smooth L1 loss between the location predictions and all default boxes that have 50% or more overlap with the ground truth annotations. The total loss is the weighted sum of the confidence loss and location loss divided by n, which is the number of matched default boxes. This allows the network to learn to modify default boxes to fit objects and predict what objects are present in each image. Here you can see the overall confidence and localization losses, which shows that our network is properly trying to reduce the loss. After training at inference time, we generate a set of over 10,000 modified default boxes during the forward pass, and then we use a non-maximum suppression to extract a small subset of high confidence, non-overlapping detections.
We use a logistic regression patch classifier. We trained this using image patches extracted from training data. So to get these patches, we went through a CSV file that was provided to us, and going through the images, we could extract these patches that we needed. We also created background patches, and we made sure that every background patch that we selected had less than 10% overlap with the objects that we also created from said CSV file. We also used k-fold cross-validation for hyperparameter tuning. For the baseline, we had a histogram of oriented gradients, so HOG, in order to grab the features from the images. We also did an image pyramid for detecting objects at different scales, as you can see in the center picture. And we used sliding window to extract patches from an image to run through the classifier at each location, and this was done during inference time. For data preprocessing, as you can see on the graph, several object classes have a majority of the images that we ended up saving. So what we decided to do was restrict datasets to only those with at least 100 boxes or 100 patches. And the final data has 134 classes plus the background class. So as you can see there in the baseline, 100 image patches per object and 600 background patches. For the SSD, we kept using the same classes. However, we didn't restrict it at 100 patches per class, so we ended up with nearly 24,000 images. The results of this for the baseline, we ended up with 9.8% accuracy, and the MAP scores were very low from what we expected and wanted, but they were 0.09% and 0.0003%. Concluding on the baseline, we predicted that our accuracy wouldn't be that good just due to the amount of data that we were sending in was not sufficient. 100 samples per class when you're dealing with 134 classes is not enough for a model to really understand the differences enough. So what we really wanted to do was use the full set, which would have been thousands per class. The sliding window also only dealt with different sizes of squares, not different aspect ratios to different rectangles, and that caused a problem in accuracy. For the SSD, we were able to learn pretty quickly, as shown in the loss graphs here that we showed previously. However, we got stuck at a local optimum, and even though we tried using restarts to get out of it, we kept getting back to the same result over and over again. So that concludes our presentation for Team 13, and thank you for listening.